Critical values are values that separate sample statistics that are probable from sample statistics that are improbable or unusual. But how do we find these critical values? It's really not as difficult as it may seem. Where do these critical values sit? Critical values generally sit right out here, and they separate our probable amount, which falls right in this value here in the hump, from our improbable values. Our improbable values are in the tails. And we need to use our normal distribution chart of z-values to find these critical values, which sit right here, and separate our probable from improbable. We base our amounts on how confident we are in our formulations. So let's use an example. Let's say we have a confidence of 90%. How can we find our critical values that separate 90% from the value in the tails? When we say we are confident at 90%, that's telling us that 90% probable is here. That's 0.90. How much is left in the tail in that case? In that case, we have 10% left divided up between our two tails. If we have 10% probability left in our tail, then we have actual 5% in each tail, because we have to divide the probability up evenly between the two tails. And if we have 10% total, we have to divide it up in half. Remember, the total probability in the curve is 100%. So in order to add up to 100%, if we have 90% here in the middle, we have another 10% to equal 100%. So we convert this to a decimal so that we can read it from our chart and find the z-score that corresponds. So we need to get our z-table and see what critical value will correspond to an area of 0.05. So let's take a look at our z-table. And if we look at the table that shows us areas in the tail, we see when we look for the value of 0.05 and get as close as we can for 0.05, we find that we can't find 0.05 exactly, but we can get pretty close. We also see that there is an asterisk at the value that is a critical value for 0.05, and that value is 1.645. If you were to take the average of 1.64 and 1.65, it would be 1.645. So the critical value that sits at 0.05 is 1.645. So if I have a bell curve that looks like this and a confidence value of 90%, then my critical value is going to be 1.645. I can follow the same procedure for any confidence level. So let's just set it up for a different confidence level. Let's assume we have something different. Let's say we have a confidence level of 95%. How would we set that up? Well, our z-scores are going to be right here, and our confidence is in here. We're confident of our probable values right in here. Well, this value is 95%. Well, how much does that leave for me to split between my two tails out here in the yellow portion? Well, that means I have 5% to split up, because 100% minus 95% is 5%. So I need to split up that 5% between my two tails. That means I have 2.5%. That means I have 2.5% in each tail. So in my z-score table, I'm going to look for 0.025 to determine what my z-critical is. looking at my z-chart for 0.025, I come down into my z-chart and I can find 0.025 right here. And that lines up with 1.96. So my z-critical for the tail of 0.025 is 1.96. So that is how you find your critical values when they are not given to you. There are several critical values that are just so common, you might as well make a note of them so that you don't have to continue calculating them over and over again. Those critical values are for the levels of confidence 90%, 95%, and 99%. So if you're dealing with a level of confidence of 90%, your z-critical will always turn out to be 1.645. If you have a level of confidence of 95%, which we've already seen, your z-critical will always turn out to be 1.96. And if you have a level of confidence of 99%, your z-critical will turn out to be 2.575. So you could make a note of those, and no need to calculate those over and over again. However, if you come across levels of confidence of other levels of confidence, then you will need to use this technique to find your z-critical to correspond to those specific levels of confidence.